Welcome to another mini-series. In our previous series, we covered the multinomial logit framework all the way from binary logit to estimating welfare. We saw how these models allow us to recover preferences using data on observed choices. But we also discovered a major limitation, and that is the independence of irrelevant alternatives property. As you might recall, the logit model enforces that the ratio between the choice probabilities of any two alternatives depends on nothing else in the model. This mathematical convenience comes at the cost of behavioral realism. In this mini-series, we're going to introduce generalized extreme value models, or GEV models. These are going to allow for more realistic substitution patterns and more credible welfare calculations. If we think back to the red bus, blue bus problem, in a prior video we showed that the logit model and the assumptions in the logit model result in strange substitution patterns between the different buses. And this is because of the independence of irrelevant alternatives property that comes baked into multinomial logit models. We see in this decision tree framework that car, red bus, and blue bus are all treated as similar goods. One way that we can get around the IIA property is to nest the choice set. So instead of having red bus and blue bus compete directly with car, we instead nest the choice set so that the car and the bus are what's being chosen, and then within the bus, we can choose the color of the bus. What this does is it maintains the IIA property at each level of the model, but it breaks IIA across alternatives that are in different nests. So what this looks like with the simple commute method model that we just talked about is that within the bus nest, we have the blue bus and the red bus are directly competing in an IIA consistent manner. And we also have that car and bus are directly competing in an IIA consistent manner. But what's not the case is that car and red bus are IIA or car and blue bus. And what this is going to do is it's going to allow for more realistic substitution patterns if, say, we introduce a yellow bus. In effect, the red bus and the blue bus are going to be treated more as substitutes. And so the probability of taking the car is not forced to change much if a new bus color is introduced. The nested logit model that I just showed you is actually the simplest of the GEV models, besides the multinomial logit. But these GEV models can also handle much more sophisticated structures than what I just showed you. What makes GEV particularly powerful is it's not just solving a statistical problem, but also a behavioral problem. With more realistic distributions on the unobservable preferences, we can tackle more realistic economic questions and come up with answers that are more pertinent to ongoing policy discussions and make more realistic predictions. The downside is that with this greater amount of flexibility comes a greater computational cost, as well as a more difficult job of interpreting the results. So it's important to keep this trade-off in mind. In this series, we'll derive nested logit from first principles. We'll also explore applications of nested logit in different domains. And we'll also cover more advanced GEV models and discuss this trade-off between behavioral realism and computational complexity. Most importantly, we'll see how departing from IIA opens us up to more realistic and credible inference, which is what we care about the most. I hope to see you in future videos in this series, and thanks for watching.